Have you ever stopped to think about the single most important invention of the last century? Seriously, it's not the car, it's not the airplane, it's not even the internet, really. It's something way, way smaller. In fact, you probably have billions of them within reach right now. I'm talking about the integrated circuit. And its story, believe it or not, starts with a problem of just pure, absolute chaos.
Just look at this tangled, smoking mess of wires. This was the absolute peak of electronics back in the day. It represented a problem so huge that engineers gave it this really dramatic name, the tyranny of numbers. Every single one of those little components had to be connected by hand, creating this incredibly fragile web that was expensive, super unreliable, and of course, physically massive.
So that's the big question for us today. How in the world did we go from that hand-soldered nightmare to the sleek, powerful devices that we all have in our pockets? Well, the answer lies in one revolutionary idea that completely changed the game.
Okay, so first things first, we need to really understand this roadblock. Before we could even dream of the future, technology had to figure out how to conquer this tyranny of numbers. It was a problem that was holding back the entire digital revolution before it even got started.
This right here shows you exactly what that tyranny looked like. On the left, that's the before picture. Early computers that literally filled entire rooms. I mean, these things were behemoths, built from countless individual vacuum tubes and other parts, all painstakingly wired together. And with so many separate pieces, things went wrong, all the time.
So, to be clear, the problem wasn't just one thing. You had these unstable, hand-soldered connections that would fail constantly. That, of course, led to frequent breakdowns. And the enormous size and cost made these machines totally inaccessible for most people. But the real kicker? This sheer complexity meant you just couldn't build anything more powerful. Progress had completely hit a wall.
All right, so the first crack in that wall came from a complete shift in thinking. Instead of building with all these fragile glass tubes and wires, what if you could do it all inside a single, solid piece of material?
And that brings us to the transistor. The name, by the way, is just a mashup of the words transfer and resistor. It was this tiny little device that could do the exact same job as a big, hot, fragile vacuum tube, but with none of the drawbacks. It was, and I'm not exaggerating, a total game changer.
So, you can see here, the transistor was incredible. No more fragile glass, no more hot filaments. It was a massive leap forward. But, and this is a huge but, it only solved half the problem. You still had to connect thousands or even millions of these tiny little things together by hand. The tyranny of numbers was still calling the shots.
So how do you solve the connection problem? The real aha moment came when two different inventors, working totally separately, had the same brilliant idea. What if you stopped connecting the parts and just built them all together on one single block? This was the monolithic idea.
And this set the stage for one of the most important races in the history of technology. On one side, you had Jack Kilby over at Texas Instruments. On the other, Robert Noyce at the brand new Fairchild Semiconductor. Both of them were trying to create the world's first integrated circuit, but they went about it in totally different ways, sparking this competition that would pretty much define our modern world.
Their competing ideas came to be known as Kilby's flying wires and Noyce's planar process. One was a brilliant proof of concept, the other was basically the blueprint for the entire future of manufacturing.
Now, Kilby's invention came first. And don't get me wrong, it was absolutely brilliant. He proved you could build all the components on a single piece of semiconductor. But the problem was still the connections. See, he relied on these tiny hand-soldered gold wires, the flying wires, and that meant it was still slow, still manual, and really prone to defects. It was an amazing invention, but you just couldn't mass-produce it.
And this is where Noyce's breakthrough made all the difference. His planar process was designed to solve the manufacturing problem right from the start. Instead of wires, he used a process called photolithography, which is basically like printing the connections directly onto the chip itself. It was fast, it was automated, and it meant you could make millions of them with consistent quality. This wasn't just another invention. This was a revolution in manufacturing.
So, long story short, while both men are rightly credited as co-inventors, it was Robert Noyce's manufacturable planar process that truly unlocked the potential of the integrated circuit. It's the foundation for every single computer chip made today.
So, with a way to finally mass-produce these miraculous little chips, the floodgates just burst open. What happened next was an explosion of computing power unlike anything the world had ever seen before.
I mean, this image says it all, right? We went from the room-sized machine on the left to the pocket-sized supercomputer on the right. The integrated circuit didn't just make things smaller, it made them exponentially more powerful and accessible to literally everyone.
And this incredible pace of progress was famously observed by Robert Noyce's colleague, Gordon Moore. Now, Moore's law isn't a law of physics, it's more of an economic prediction. He basically saw that the number of transistors on a chip, and by extension its performance, was doubling about every 2 years. This observation became a kind of self-fulfilling prophecy, driving the entire industry to keep innovating at this blistering speed for decades.
The results are just staggering. Performance shot up by billions of times. At the exact same time, the cost and the size just plummeted. That's the real magic of the integrated circuit. It made things unimaginably better, cheaper, and smaller all at once.
You can see its legacy right here. Every single major technological shift of our lifetimes stands on the shoulders of the integrated circuit. The PC revolution, the internet, the mobile age we're living in, and now the AI era, none of it, absolutely none of it would be possible without this one invention. It's the physical foundation of our entire digital world.
So, when you step back and look at the whole picture, the impact of this one tiny device is almost impossible to overstate. And that brings us back to the central idea of this whole explainer. We call the integrated circuit the smallest brick because, just like a simple brick can be used to build a skyscraper, this single tiny component is the fundamental building block of our entire complex, interconnected digital world. Ultimately, that's what it is, the bedrock. From how we communicate and get our healthcare, to our entertainment and our science, every single part of our modern information society is built on the silent, tireless work of billions and billions of these integrated circuits.
And that leaves us with one final, pretty fascinating question. The integrated circuit tamed the tyranny of numbers, and it built the digital age. So, as we look ahead to new challenges in things like quantum computing, biotechnology, and whatever's next, what do you think will be the next smallest brick that changes our world all over again?